Picture this, you're walking through a modern city, admiring the sleek glass towers reaching towards the sky. What you're actually looking at is the work of some of the most specialized engineers you've probably never heard of. These aren't your typical structural engineers or architects, these are facade engineers. And their job? Well, it's surprisingly complex. They're the ones making sure that massive glass walls doesn't turn your office into a greenhouse, that birds don't fly into it at 30 miles per hour, and that pigeons don't turn your building sledges into their personal penthouse suites. We're talking about a profession that includes building physicists who can tell you exactly how much heat will leak through the wall joint, material scientists who specialize in roof glazing that can survive hurricane-force winds, and yes, even ornithologists who design strategies to keep pigeons out while providing cozy nesting spots for swifts and bees. There are facade acousticians who ensure the city's noise doesn't turn your living room into a concert hall, and glass gurus who can engineer everything from bulletproof barriers to safety glass that breaks in just the right way. The industry even has its own supply chain consultants and commercial managers, because apparently even windows need business strategy these days. Here's might surprise you. This industry is worth over $363 billion globally and growing. That's comparable to the entire GDP of Finland or Vietnam. And you probably didn't even know it existed. To understand how facade engineers evolved into this soon-to-be $500 billion industry, we need to take a journey through architectural history. This is the story of engineering problems where solving one challenge inevitably creates 3 new ones to tackle. My name is Eugene Korch. I am a practicing facade engineer and I teach facade engineering at the Institute for Architectural Science and Technology. And today we are diving deep into the world of facade engineering. What are its roots? What do these engineers actually do? And why this profession is more critical than ever. Let's start at the beginning. For most of human history, facades weren't engineered, they were just walls. And not just any walls, these were walls that literally held up the building. Think about it, walk into a medieval cathedral or an ancient Roman structure that is still standing today. Those massive stone walls, they weren't just keeping the weather out, they were the skeleton of the entire building. The floors rested on them and the roof was supported by them, and if you removed them, the whole structure would collapse, faster than a house of cards. This all changed in the early 19th century with the revolutionary material, reinforced concrete. Suddenly, we had this grid of concrete columns and slabs that could do all the heavy lifting. The walls were liberated from their structural duties and could now hang from the building's framework, like curtain. And that's exactly why they started calling them curtain walls. Now you might think that this made things easier for the facade design. After all, if the wall no longer has to hold up the building, surely its job becomes simpler, right? Well, not quite. See, those old masonry walls were actually pretty good at their job, even if they were doing it in the most brute force way possible. Let me explain what I mean. Traditional mass walls, thick stone or brick construction, were essentially nature's Swiss Army knife. They handled everything through sheer mass and thickness. When it rained, they would absorb some water, but the wall was so thick that the moisture rarely penetrated all the way through. When it was sunny, the thermal mass would moderate temperature swings. When there was noise outside, the sheer mass of the stone kept most of it out. These walls were thick enough to park a car in, which made them excellent at dealing with sound, weather, and structural loads all at once. And because they were so thick, windows openings were relatively small, which meant overheating was rarely an issue. You actually wanted as much light as possible. The architect's main job was simply to keep direct rain off the walls with overhanging roofs and well-designed sills and ledges. That was pretty much it for the facade engineering in the medieval area. But once facades were freed from structural duty, structural engineers started backing away from the facade design. After all, the wall's only structural job now was to hold itself up and not to fall off the building. That's when the first architectural technologists and the facade specialists began appearing in the industry. They had the new challenge. How do you make lightweight wall perform all the jobs that the meter-thick stone wall used to do? The answer seemed to be obvious at first. If the old walls worked by being thick and porous, why not go the opposite direction? Make walls thin, light, and completely impermeable. Enter the perfect barrier concept. Material science wasn't just advancing in concrete. The glass industry was revolutionizing too. Suddenly we could produce glass panels that stretched nearly from floor to ceiling. Combined with lightweight steel frames, we could create buildings that were essentially transparent boxes. Glass seemed like a perfect material for this new approach. Unlike masonry, it doesn't absorb water at all. It is completely non-porous. In theory, if you could seal it properly, you would have a wall that would never leak. The early curtain wall pioneers were optimistic. They had these elegant grids of steel mullions and transoms holding massive glass panels, all sealed with glazing putty. It looked revolutionary, it felt modern, and it was going to change the architectural industry. There was just one small problem. It didn't work. Those early glazing putties weren't elastic. They were rigid, and buildings move a lot. They expand and contract with temperature changes, they sway in the wind, and they settle over time. The putty cracked, the seals failed, and suddenly these perfect barriers were leaking like sieves. And when they leaked badly. Unlike those old stone walls that could dry out slowly, these sealed systems had nowhere for the water to go once it got in. The first generation of curtain walls became notorious for their leaks and water damage. It took several decades before polymer science caught up with the architectural ambition. We needed to develop membranes, gaskets, and silicons that could move with the building while maintaining their seals. But even then, we had another problem. These early all-glass facades were essentially single-pane windows covering entire buildings. They had no thermal mass, no acoustic performance, and they turned buildings into greenhouses in summer and freezers in winter. The perfect barrier was proving to be perfectly imperfect. Faced with the persistent failure of sealed systems, facade engineers had a revelation. What if we stop trying to keep water out completely and instead focus on managing it when it inevitably gets in? This philosophical shift led to one of the most important concepts in modern facade engineering, the rainscreen. The rainscreen principle is beautifully simple. Instead of one barrier trying to do everything, you create multiple layers, each with a specific job. The outer layer, the rainscreen, takes the brunt of the weather and does its best to keep water out. But behind it there is a cavity, and behind that there is a second barrier. Here's the clever part. When the water gets past the first layer, and it will, it hits the cavity. But the wind pressure that drove it through the first layer can't push across the cavity to the second layer. The water just drains down the cavity and exits at the bottom, while any moisture that remains evaporates and ventilates out. It's like having an umbrella and raincoat. The umbrella, the rain screen, handles most of the rain, but when some gets through, the raincoat, the inner barrier, keeps you dry. This concept wasn't entirely new. Scandinavian timber builders had been using cavity walls for centuries, and British builders were using them in low-rise masonry construction in the early 20th century. But it took the spectacular failures of early curtain walls to make the industry embrace this water management approach. The beauty of the rainscreen systems is that they are forgiving. They expect water to get in, they are designed to handle it, and they can dry out naturally. This was the fundamental shift from the perfect barrier mentality to the water management approach. But just as facade engineers were getting comfortable with rainscreen systems, another challenge emerged that would force them to rethink everything once again. The 1970s fuel crisis changed everything. Suddenly, heating and cooling costs weren't just operational expenses. They were a major economic factor. Buildings that had been designed without much thought to energy efficiency were bleeding money through their facades. This introduced an entirely new parameter to the facade design: thermal performance. Engineers now had to think about U values, thermal resistance, and heat transfer coefficients. For the first time in their architectural history, keeping the heat in or out became a primary design consideration. It might surprise you to learn that insulation is actually a relatively recent invention in construction. Throughout most of human history, we didn't really think about heat loss through the walls. Buildings were heated by fireplaces, which were expected to heat the air in the room, with the walls simply containing the warm air. The concept of thermal resistance had been described by French physicists in the mid-19th century, but it took the stock market crash of 1929 and the subsequent Great Depression and the energy crisis of the 70s to really drive home the importance of energy efficiency. Even then, insulation was mostly seen as a retrofitting solution. You'd blow insulation into existing wall cavities and add it to voids in between the stud walls. The transformation was remarkable. In North America, adding insulation was reported to reduce fuel bills by up to 30% and make homes up to 7 degrees cooler on the hottest summer days. But here's what really changed: our expectations of comfort. Today, we expect to wear the same clothes at home all year round. We set the thermostat to 21 degrees and expect it to stay there, regardless of whether it's snowing or blazing hot outside. This concept of constant room temperature would have been completely alien to anyone living just a century ago. They wore warm clothes in winter and light clothes in summer, and they adapted to seasonal temperature changes. Today we rely on our building envelopes to create perfect internal environment all year round. This shift in expectations created an entirely new field with facade engineering, building physics. Suddenly, engineers needed to understand not just how to keep water out, but how to control heat transfer, manage thermal bridges, and prevent condensation. Adding insulation to walls seemed like a straightforward solution to energy efficiency. Fill the cavities and voids with insulation material and voila, better thermal performance. But as it is often the case in facade engineering, solving one problem creates several new ones. The issue was the water vapor. Water doesn't just travel through the building materials as liquid. It can move through them as vapor, and when that vapor hits the cold surface, it condenses back into the liquid water. With insulation filling the wall cavities, the dew point, the temperature at which vapor becomes liquid, suddenly coincided with the sheeting boards inside the wall. This meant that moisture from inside of the building was condensing within the wall's assembly, where it couldn't escape. The result? Mold growth and structural corrosion. Buildings that looked fine from the outside were literally rotting from the inside. This crisis gave birth to a new subspecialty, building physics. Building physicists analyze the permeability of different materials, their thermal resistance, and how they interact when combined in wall assemblies. They consider buildings' use, local climate, and seasonal variations in design wall systems that can handle both thermal and moisture performance. More recently, Joseph Stiburek popularized the concept of the perfect wall, though the concept had been in use for decades before he gave it a name. The perfect wall concept is elegantly simple. Put all your control layers, air barrier, water barrier, and thermal barrier, on the outside of the structural wall. Picture this. You start with a concrete or masonry wall, you cover it with a membrane that serves as both air and water barrier. Then you add a continuous layer of insulation. Behind that, you create a drained and ventilated cavity. Finally, you add your cladding, brick veneer, metal panels, or aluminium composite material cladding. This system works because the structural wall stays warm. It's on the inside of the insulation layer, which means you virtually never had to worry about interstitial condensation. The membrane keeps air and water out, and the insulation controls heat transfer, and the cavity manages any moisture that does get in. It's cheap, effective, and works in almost any climate for almost any building type. It seems like facade engineers had finally cracked the code. But remember when I said earlier about solving one problem, creating new ones. The perfect wall had a dark secret that wouldn't become apparent until much later. The cavity that makes the perfect wall so effective at managing water also makes it dangerously effective at spreading fire and smoke. Air moves through these cavities, and unfortunately, so can flames. When you combine combustible insulation with combustible cladding and add a ventilated cavity, you've essentially created a chimney effect that can spread fire vertically through a building at terrifying speed. The tragic fires at Grenfell Tower in London and Campanar building in Valencia were devastating examples of what could happen. Both buildings featured the classic perfect wall assembly, insulation on the outside, ventilated cavity, and composite cladding. These disasters forced the industry to confront an uncomfortable truth. The wall systems that solved thermal and moisture problems so elegantly had created a potentially deadly fire risk. This revelation created yet another sub-speciality in facade engineering, fire safety. Engineers now had to find ways to maintain the benefits of the cavity walls while preventing fire spread. For example, one of the solutions involved compartmentation, breaking up those continuous cavities with fire barriers. These barriers use intumescent material that remains open during normal operation, allowing ventilation and drainage, but expands and seals the cavity when exposed to fire. Modern facade fire engineers also work with fire-rated glazing, automatic smoke vents, materials reaction to fire properties, and spandrel area geometry, among other things. It is an entire field of engineering that barely existed 30 years ago. While building engineers were wrestling with wall systems, the window and curtain wall industry was undergoing its own revolution. World War II had pushed aluminium and polymer technologies to entirely new levels. Gone were the days of simple steel sections and rigid glazing putty. Now engineers could extrude elaborate aluminum profiles and seal them with sophisticated rubber gaskets and elastic silicons. This allowed the curtain wall industry to miniaturize the cavity wall concept. Modern windows and curtain wall profiles are essentially tiny rainscreen systems with elaborate internal geometries designed to manage water. These aren't just frames holding glass. They are complex labyrinths with multiple chambers, drainage channels, and thermal breaks. They feature two-stage sealed systems where the outer seal keeps most of the water out, but any water that does get in is captured and drained away through the internal cavity system. The advancement in glazing technology was equally impressive. We can now fabricate glass panels the size of truck trailers, making the floor-to-ceiling glazing routine rather than exceptional. But these advances created new problems. All glass facades might be watertight and airtight, but they are also very light, which means they have virtually no acoustic performance. Sound travels right through them, and worse, those hollow aluminum profiles create perfect sound transmission paths between floors and neighboring apartments. Acoustic performance became another critical consideration in facade design. Engineers had to learn how to interrupt sound transmission paths by splitting mullions, filling them with acoustic inserts, or encapsulating them internally. For external noise control, the solution came from advances in glass technology. Laminated glass, multiple glass layers bonded with acoustic film, provided mass and vibration dampening. Insulated glass units with asymmetrical glass thicknesses and inert gas-filled cavities further improved acoustic performance. Of course, these innovations weren't developed solely for acoustic reasons. Laminated glass was primarily a safety feature, ensuring that broken glass stays in place rather than falling. Insulated glass units were designed for thermal performance, with inert gas fills providing superior insulation. Lamination and thermal treatment allow glass to become structural. Modern glazing can handle wind loads, support its own weight, and in some cases even support parts of the building structure. Glass went from being a simple infill material to being a structural component. With unlimited glass sizes and improved performance, all glass facades became ubiquitous, especially on skyscrapers. But this has created what might be the biggest challenge facade engineers have faced: solar heat gain. After all, the world's first all-glass building were greenhouses. Glass facades were great for growing tomatoes, but they are terrible for office buildings, especially in hot climates. The cost of cooling these glass boxes in desert cities is astronomical. The solution required advances in chemistry and material science. Modern glass coatings, created from a combination of precious metals and chemicals applied during various stages of glass manufacturing, can dramatically reduce solar heat gain while maintaining transparency. These coatings gave us those distinctive gold, blue, and green glass buildings from the 80s and 90s. Thankfully, coating technology has advanced to the point where high-performance glass can look completely clear to the human eye. But even the best coatings aren't enough. The ultimate solution combines everything we've discussed: thermally broken aluminum profiles, high-performance insulated glass, and automated solar shading systems, all integrated into double-skin facades where the shading operates in the cavity between two glass systems. Modern facade engineering has essentially become aerospace engineering for buildings, designing systems that must operate flawlessly, high up in the sky, for decades, without the possibility of landing for maintenance. Speaking of maintenance, this brings us to another specialized field: facade access engineering. Unlike an airplane that can return to a hangar for service, building facades must be cleaned and maintained in place, often hundreds of feet above the ground. Every facade design now includes a comprehensive maintenance strategy. This might involve building maintenance units suspended from the roof, provisions for rope access, or integration of motorized platforms. Some buildings even incorporate tracks or anchor points directly into the facade system. Facade access engineers design these systems to ensure that every component of the facade can be reached, cleaned, and replaced throughout the building design life, which is typically 60 years or more. All glass facades created unexpected environmental problems, for example bird collisions. It's estimated that up to 1 billion birds die annually from the colliding with buildings only in the US. No, I have not misspoken. 1 billion. They either mistake reflective glass for sky and trees, or they simply can't see the transparent glass barriers. And this led to another subspecialty: facade engineers who specialize in bird-friendly design. They use fritted glass patterns, external solar shading screens, and other strategies that make glass visible to birds while maintaining human view. But facade engineers go beyond just preventing bird strikes. They are now designing swift nesting boxes, bee bricks, and other features that create urban habitat for wildlife. At the same time, they are developing deterrent systems to keep pigeons and other pests from roosting in facade cavities. It is a delicate balance of urban ecology engineering that requires understanding both building physics and animal behavior. The most recent and perhaps most urgent challenge facing facade engineers is sustainability and carbon footprint reduction. The construction industry is responsible for a significant portion of global carbon emissions, and building facades are a major contributor. This has created another new subspecialty, sustainability-focused facade engineering. These engineers must balance all the performance requirements we have discussed while minimizing embodied carbon in materials, maximizing energy efficiency, and designing for disassembly and recycling at the end of life. It's not just about choosing lower carbon material, it's about optimizing entire system to minimize lifetime environmental impact while maintaining all the other performance requirements. As you have probably figured out by now, we have made quite a few mistakes along the way. Millions of buildings from the 20th century are approaching the end of their design life. Buildings with single pane glass, no insulation, and questionable water management. Demolition isn't an option. The embodied carbon in existing structures represents decades of industrial production we cannot afford to waste. Plus, many of these buildings have cultural and architectural significance. This creates two new subspecialties in facade engineering: retrofit facade engineering and forensic facade engineers. Retrofit engineers solve an impossible puzzle, bringing aging buildings to modern performance standards while often maintaining their original appearance. You can't add external insulation to a listed building, so we have developed smart vapor permeable membranes for internal insulation that prevent condensation problems. Those energy hemorrhaging single glass windows are dealt with vacuum insulated glazing that fits existing frames. Forensic facade engineers are the detectives of the industry. They investigate facade failures, analyze aging materials, and determine what's salvageable versus what needs replacement. They are often working with materials and systems no longer manufactured, essentially performing buildings archaeology. And the irony is, retrofitting often requires more innovation than new construction. You are solving problems that weren't anticipated when the building was built, using technologies that didn't exist then within the constraints that would never be accepted today. But when it works, a retrofit can extend a building design life by 50 years while reducing energy consumption by 80%. That's engineering impact worth celebrating. Finally, we come to perhaps the biggest challenge of all: global housing crisis. Nearly every country is facing housing shortages, which means we need to build faster and cheaper while solving all the technical problems we've discussed. This creates a fundamental tension in the facade industry. The industry has become incredibly sophisticated, but that sophistication comes with complexity and cost. Engineers must now find ways to simplify systems without compromising performance. The most tragic part of this challenge is that most people don't even know the facade engineering industry exists. This is a $363 billion global industry comparable to the entire economy of Finland, growing at 8% annually towards the $673 billion by the 2032. Yet there are relatively few people in the industry, and even fewer educational programs. Universities offering facade engineering qualifications globally can be counted on two hands. We are facing a massive skill shortage just as the challenges become more complex and urgent. And this is why we at the Institute for Architectural Science and Technology are working to expand education and awareness in facade engineering. If you are an architect, structural engineer, or mechanical engineer, consider exploring this field. The industry desperately needs skilled professionals who can tackle these complex, interconnected challenges. Facade engineering represents one of the most interdisciplinary fields in construction. It combines structural engineering, building physics, material science, environmental science, fire safety, acoustics, sustainability, and even biology. It is a field where solving one problem inevitably creates new challenges, requiring constant innovation and adaptation. The next time you walk past modern buildings, take a moment to appreciate the incredible complexity hidden behind the seemingly simple facade. It's not just a wall, it's a sophisticated system engineered to control water, air, light, sound, and fire, while providing views, natural light, and environmental integration. To dive deeper into facade engineering, consider subscribing to our channel and checking our Facade Intelligence platform, where we offer courses on each aspect we've discussed today, along with the projects, case studies, industry insights. Thank you for joining me on this journey through the fascinating world of facade engineering. Until next time, keep looking up and remember, those facades are more complex than they appear.